08 to 09. So without further ado, Mr. Al Khowaiter, the podium is yours. We look forward to
Thank you very much. Good morning, good afternoon, and good evening for some, I assume. Great to be here. It's a great honor to speak to this audience on a topic which I think has been a difficult topic over the last few years, as more and more of the media has kind of demonized one of the most important, and I believe, processes in industry and for the world, actually. As we know, combustion drives 99% of our transport sector. It has a huge share of energy production around the world. And the importance of combustion as a science and as an industry or as a technology cannot be underestimated. And its importance and sustainability and its efficiency especially have to be priorities for the world. And I'm really glad that there are scientists and for to be speaking to this symposium because of the criticality of this and the lack of attention that's been given to combustion over the last few years only, although I think many stakeholders recognize the importance of going forward. Can I have the next slide, please? Advance the slide, please. See if I can. Okay. So as this slide shows, the primary energy demand, global primary energy demand, continues to increase. We are seeing, of course, demand decline in power, in buildings and passenger vehicles, of course, with alternative technologies, renewable energy and such. But the reality is that it's more than offset by growth elsewhere, and this is mainly in the non-OECD countries. Although we see demand plateauing and declining even in many OECD countries, the rest of the world, it continues to grow due to the drivers of economic growth. And as we can see here, under the IEA stated policy scenario, there are many drivers for that. We can see aviation shipping, because of the difficulty of decarbonization, will continue to grow for oil demand. And I'm looking specifically at oil demand. We see petrochemicals as a huge growth area for oil, although that's not a combustion related. And we see also several other areas where we think that there will be additional demand. And even in the policy scenarios we see, basically internal combustion engine vehicles will continue to continue to grow, in fact. Conventional cars will continue to be a large share of the vehicle stock through 2040. In this analysis here, we can see that conventional car sales may peak by the late 2020s, but even by 2040, they still a very large share. And by 2050, we will see transport is still going to constitute a lot, it will actually increase its share of global CO2 emissions because of that. So energy efficiency is an essential element going forward. And we expect that most of, in fact, of the reduction in emissions will come from energy efficiency. But in a carbon-constrained world, the biggest challenge is how do we reduce that climate concern of additional CO2? How do we hold the global temperature rise to well below 2 degrees C? How do we reduce those CO2 emissions? And with 24% of that coming from transport, we are expected in the transport sector to deliver about 20% of that reduction. And as you know, the Paris Accord requires each sector to reduce its carbon footprint. And as I said, for example, here, EU transport emissions represent 24%, and their expectation is that there will be deep decarbonization across that sector. So the challenge is, how do we address this dual challenge of meeting the growth of the economies of the world and reducing their emissions? And of course, it requires several policy options and technology options. Many of the opportunities are actually in avoiding the need. And as you see this framework here, it's a common framework, well-known framework, of avoiding and shifting and improving. I'm going to focus today on improve, which is really improving the use of the energy and especially efficiency, as well as alternative. So the challenge is really meeting the most challenging targets, which is meeting EU decarbonization ambitions. And so if you look at the options that the EU is looking at, and we have looked at them, much opportunities are there. There's a lot of opportunity in efficiency and hybridization, but that will only get us, in the case of light-duty vehicles, about 30% of the way there. Similarly, for the heavy-duty sector, we see about 20% improvement in efficiency and hybridization, for example. The rest of the way is got to be met with either electrification, fuel cell electric vehicles, or a new topic, I think, relatively recently, is the renewable fuels. And for aviation and marine, I think the best chance, of course, are renewable fuels and offsetting, which has been recognized by the International Civil Aviation Authority. And for marine, we're actually looking at mobile carbon capture, for example, as a potentially competitive option, as well as other fuels such as ammonia and hydrogen. So the point I wanted to make here is that even in a decarbonized world, our best options may not always be electrification in the traditional sense, but in fact, renewable fuels may play a big role in being able to decarbonize the transport sector. If we look at EU transport options, if we see by 2050, we think there needs to be about 3.7 gigatons reduction by 2050 of CO2 emissions from the transport sector. And if you look at two different options, if you did only electrification and no internal combustion engine sales after 2030, that's one option. But you could achieve the same decarbonization options by introducing a mix of renewable fuels as well as hybrid electric vehicles and electric vehicles at perhaps a lower cost and say a less of an infrastructure challenge. So renewable fuels may offer an opportunity really to address this decarbonization. And here's a presentation by FEV, which showed the renewable fuels potential to up to 1/3 of CO2 savings by utilization of renewable fuels. So what are renewable fuels? Renewable fuels are the concept of taking CO2 from the atmosphere and combining them with renewable hydrogen and combusting them like any other fuel. And here we see CORSIA, the International Civil Aviation Authority program for basically reduction of CO2 footprint. This organization or this program seeks to reduce emissions from the aviation sector by 50%. Much of that will come from offsetting, but also from biofuels and also what are called sustainable aviation fuels that would be renewable. Just to compare the carbon footprint of synthetic fuels, we see about 1/8 of the carbon intensity of oil-based fuels, roughly. So if you look at an oil-based fuel in the range of 350 to 400 kilograms of CO2 are emitted when you over the full life cycle of a barrel of oil, for example, oil-based fuel. About a quarter of that is emitted in the process of advanced biofuels, actually much more for what the conventional existing biofuels. But for advanced biofuels, which are in being developed as we speak, about a quarter of that, say maybe 100 kilograms per barrel equivalent. And then finally for synthetic fuels, it's an eighth of that, which would be about 50 kilograms per barrel of fuel used. So it's a very impactful in terms of carbon intensity by having these drop-in fuels that could be mixed with existing fuels initially because of the cost, but ultimately, as costs go down, could be the base fuel utilized in combustion. And they are technically feasible. They've been proven in many pilot projects. There are a number of projects actually as we speak. One in Chile today looks to develop synthetic fuels from wind power and hydrogen production from electrolysis combined with CO2 from the air atmosphere. And so these pilot projects, we think, are scalable, and that, of course, the viability will depend on the costs, but we think that they're quite competitive compared to alternative means of decarbonization of the transport sector. And one of the reasons that we believe that it will be competitive is because of the maturing of the technology. Electrolyzer technology, as you know, has been in the news lately because of the hydrogen economy concepts. And we also see electrolysis and competitive hydrogen by the 2030s, early 2030s. We see hydrogen basically from electrolysis and the best renewable energy sources to be matching blue hydrogen, which would be basically the production of CO2-free hydrogen from fossil fuels. We think those two will probably meet in the 2030s, early 2030s. Electrolysis hydrogen will probably match the cost of decarbonized carbon capture with methane, for example, in the cheapest methane locations. So that would be an amazing result, which would allow basically electrolysis and renewable energy to compete for liquid fuels ultimately. The big challenge, of course, many are questioning the viability of direct air capture, and I have to admit myself, I was a skeptic in direct air capture until a number of recent pilots have been conducted over the last few years, demonstrating that it is possible to bring down the cost of capturing CO2 from the atmosphere to practical costs. We think that it is achievable to reach $100 per ton with the technologies available, which makes actually quite a competitive liquid fuel from synthetic e-fuels. Because CO2, as you know, the carbon is about a third of the CO2 requirement has about a 1/3 effect on the cost of the synthetic fuel, the CO2 requirement. So it can be, it's not the biggest part. The biggest part is actually the energy needed to produce the hydrogen. So it's quite an interesting fact that the economics are not as driven by the CO2 capture as much as they are by the H2 production. And therefore, even at those high costs of $100 a ton of CO2 direct air capture, today, of course, I have to say it's in the $400 to $600 a ton, as we've seen in pilots for CO2 direct air capture. But we see a path to $100 in the near future, and so that's exciting. And it doesn't, $100 would be quite attractive for production of liquid fuels from renewables. And of course, the question always comes about efficiency. In the end, economic efficiency trumps process efficiency. You know, we have been running gasoline, light spark ignition engines at 25% efficiency for almost 100 years, although there has been diesel available at 40 and above % efficiency. Well, the reason is it's cheaper. It doesn't. It's more elegant to have a more efficient process, but in the end, the consumer cares about the cost, and so discussions around overall process efficiency really are very nice and academic when it comes to the market at the end of the day. So, if it works and is cheap enough, it will win the market. So that's my point on this. And I understand the long-term overall process efficiency of synthetic fuels doesn't look as good as other fuels, but in fact, what matters is the price at the pump. And of course, there is, as I said, there is an efficiency disparity if you take renewable fuels and utilize them in a battery electric vehicle versus using them as a liquid fuel, much lower efficiency. I have to say two things. One is the efficiencies along the chain of the synthetic fuels are improving because it's a very immature technology at this point. So we expect electrolyzer efficiency to really rise from the 60s and 70, where it is now, to probably the 80 and 90 in 10 years' time. 90% efficiency is probably a good number ultimately for the peak of electrolyzer efficiency. And then for the processes to go from hydrogen to liquid fuels, we also expect efficiencies to rise there. So we will see an improvement probably into the range of the competition with fuel cell electric vehicles, which are already economic in some markets. Of course, in order for them to work, they have to be recognized by policymakers. And at this point, it's still early in the rules and regulations that are being established in the different markets. But I think there is a beginning. We're seeing in Europe a recognition of e-fuels. The International Civil Aviation Authority has also given, I would say, a green light to the development of e-fuels in the form of the CORSIA regulations for the sustainable aviation fuels. So I think their policy is moving in that direction. I think as industry starts developing more and more pilots, we see the one in Chile, we'll be seeing probably in NEOM as well, similar project in Saudi Arabia, and other locations. As we develop these synthetic fuels and show their competitiveness and their flexibility, I believe policymakers will respond and regulators will recognize the benefits. So just to kind of compare synthetic fuels, we can see that here we've shown biofuels, conventional biofuels, in a cost per ton. Now, I want to emphasize that this really isn't normalized. Well, in the sense, this is a cost per ton. But in fact, when you normalize for energy, or even better, normalize for carbon footprint, which is the main purpose of introducing e-fuels, there's a tremendous advantage of e-fuels over the other fuels that are shown here. So, for example, we see that advanced biofuels are quite expensive to produce. They have lower carbon footprints, but e-fuels actually have half of the carbon footprint of the advanced biofuels. And so if you normalize for CO2 mitigated, the difference is even more dramatic. You see the e-fuels will have a much lower cost per ton of CO2 mitigated. And of course, the conventional biofuels are terrible in that sense. They look low cost today, but in fact, because they have quite a significant carbon footprint, they would be a much higher cost of mitigation, doubling or tripling what you see here relative to the e-fuels. So I think maybe this diagram, we could have done it on a CO2 basis, might have been more dramatic. And I think it's something we can discuss as well in the question and answers. So the challenge, of course, is really coordinating this triangle of government, policymakers, the fuel manufacturers, and the automakers. As usual, starting a new market is a chicken and egg kind of situation. You need to have the infrastructure in place. You have to have the fuel before you can do the engines. The engines won't be made unless the government has regulated and allowed the fuels and the engines to be made. So it's a big challenge. We see a lot of ways of doing this. It will need consortiums of say, automakers and fuel manufacturers to collaborate with government support to be able to utilize the credits from fuels, synthetic fuels, to be able to meet the standards that governments set on CO2 regulations, just as they use today credits from the battery electric vehicle manufacturers. Of course, initially, we would see this as being a low carbon blending fuel. And here I'm showing two projects we're working on, one with Repsol, where we are looking at developing synthetic fuels in Europe using renewable energy. and using it as a blending fuel to allow reduction of CO2. So there's a number of projects we're working on, both on synthetic diesel and aviation fuels, as well as synthetic gasoline, which we'll be announcing in the future. The interesting thing about synthetic fuels is not only are they interesting from the point of carbon footprint point of view, but they're also very interesting from the design and the minimization of criteria pollutants, because we can design these fuels the way we want in many ways, as much as possible. They're to a limit of the chemistry, of course, but we can design them differently from what we would get in what we call the traditional fossil fuel. So we can improve certain parameters, lower NOx, for example, to help lower NOx, increase oxygenates. There's a number of different design parameters that can be influenced in the processes of methanol to gasoline or Fischer-Tropsch or the other newer processes that we're looking at as well. So there's a lot of potential to kind of leverage that combustion research to look at high quality fuels and of course reduce after treatment. And the challenges there, of course, are catalyst synthesis and applying some of the new tools, fuel design tools that allow basically simulation of the whole process of design from end to end. So we can design the fuel to match the engine architecture and simulate all of that process quickly and efficiently. So to end, we need more mobility, we need less CO2. And we believe it's going to take a mixture of powertrains. We don't think there's a silver bullet for this. We think that combustion will play a major role going forward. I think the optimism around other powertrains in the transport sector has been probably beyond. It is true. I think there's a huge need for electrification as we go forward because it does add a lot of efficiency to the energy system in general. But there are corners, or I would say large parts of the energy system, in transport especially, which are out of the existing performance envelope of electric vehicles. And it will take a lot to get there. And I think many people who are kind of extrapolating the growth curves are not familiar with those particular performance boundaries, I would say, of the existing battery technologies. Now we know battery technologies are being developed continuously, but the fact is there will be a long time before we see some of these leave the lab, and I think that it's going to take a while. And the best thing we can do is actually improve the combustion efficiency and combustion performance as we go forward. So we call out, of course, on policymakers to establish a framework for the introduction of basically a level playing field to allow a kind of technology agnostic policy, which would allow the technologies to compete on the target of reduction of carbon footprint and emissions. And I think tailor-made e-fuels can be the solution in many cases. Thank you.
Thank you very much. Am I on?
Yes.
Wonderful. Thank you. Well, on behalf of the Combustion Institute and the audience, please allow me to express our gratitude and appreciation to you for coming to give us this inspiring and informative talk. I was very inspired that Saudi Aramco is giving towards helping this transition towards a low carbon or decarbonized world. So while I'm still waiting for some questions for you, perhaps let me ask you one question that I had in mind. But in most of the roadmaps to decarbonization and emission reduction that you show, the vertical axis in my mind are all clear. That's the desirability. The x-axis is the time, and that measures in many ways feasibility. Between these two things, of course, a lot of things can happen in the next decade if we just look at the Euro Green Initiative. Between the desirability and the feasibility, how does Saudi Aramco, a major influential oil company, handles the uncertainty associated with the x-axis?
So, yeah, it's a great question. And in technology development in general, it's not just in, of course, our transport technology. Perhaps in the transport technology, and in fact, the sustainability sector overall, it's probably the most challenging in terms of this prediction, because we are taking on very immature technologies in sustainability. We're taking on technologies that we don't have the time scales. In our traditional business, for example, in the process technology side, on the refining and chemical side, we normally have about 20 years. We normally plan about 20 years from the concept to the final, say, the commercial deployment. And that's a reasonable time frame and a very profitable time frame. But in today's sustainability challenge, we don't have 20 years. We really have to address issues which are changing year by year. We're seeing tremendous change from one year to the next. And how do we advance that technology? Which it's a real challenge. And but we have some tools at I mentioned some of the tools that we have to mitigate or to address that challenge. We really do need to move to a more data-based technology development process. And we're doing that as we speak. We have, for example, we have a high throughput testing facilities, which are basically utilizing robotics and computers to basically develop or to do the experiments that we would have done in a period of 6 months. We do them now in days and weeks rather than months. So we're compressing the timeline of development of technologies, and everyone has to do that basically across the board. So in the fuel area, for example, we mentioned that we are using high throughput for example, for the catalyst development. Our high throughput facilities allow us to develop new catalysts. Those catalysts allow us to test much more quickly than we used to in the past to develop, for example, new processes that could develop new fuels. In the engine technology, I mentioned the simulation tools that allow us to simulate, for example, the engine performance on paper long before you get to a test stand. And therefore, we can cycle through opportunities and options for testing of new combustion strategies. And this is an area which has only been enabled recently, given the chemistry was a big challenge in the past. And now with better chemistry, basically kinetic models that we have, we can actually simulate that much closer to never ever going to an engine test stand and actually simulating the full engine performance. So this is the kind of tools coming together, basically AI-based and computer-based technologies that allow us to accelerate the trial and error process that was experimentation in the past, and really bring a technology much closer to market. But there are, I say, once you've got a prototype up and running, you've still got to go through the typical market introduction challenge. And that risk is very hard to overcome. And the time, as you said, the x-axis, is hard to predict. And so how do we mitigate that challenge? I think we have to do it through collaboration and consortiums of like-minded companies who see this challenge. We've done something similar in the oil and gas industry. So we established the Oil and Gas Climate Initiative. And that initiative looks at how to collaborate on developing solutions to reduce the carbon footprint of the oil and gas industry, both our own operations and our product footprint. So this collaboration mitigates the risk and accelerates the entry to market of technologies that we've invested in jointly. So through our climate investments platform, it's a venture arm of the Oil and Gas Climate Initiative. We invest in a number of technologies. We help to de-risk the market entry of those technologies by piloting them through the consortium of oil companies. And this accelerates its adoption across the industry. I think those are the kind of models we need to apply in the auto industry as well, and transport. These are risky technologies. One company on its own will not be able to accelerate that, the introduction of these technologies. We need to be able, for example, in the synthetic fuels, I mentioned the project. Each of these projects, synthetic fuel projects, is going to take a number of companies. I realize, or I read on the Chile project, Siemens, I believe Porsche, a number of other companies are collaborating to bring that project to light. And so this is the kind of work that needs to happen. It needs to be consortiums of companies, government support to accelerate these timelines. Because of the challenge that we face is not a multi-decade challenge. It's really, if we don't do something in the next 10 years, it's not achievable. The targets the Paris Accord has set are not achievable. So this is going to require a different kind of acceleration in sustainability.
Very well. So what I want to say is this research community is ready to help you and industry by and large to achieve that goal. So it's very inspiring to me to hear your analysis. And so we have a couple of questions from the audience. Let me go in the order of how we receive it. The first question is from Katrina Collinghouse. She is the hotel lecture speaker of this conference. The question is, could you let us know about the potential infrastructural changes around your investment in electrolyzer, renewable power, etc., and about the governmental policy change in your country?
Yeah. So, let me start with the country. The country has been, I guess, promoting renewable energy for a long time, but we haven't seen, of course, large projects in the Kingdom of Saudi Arabia developing due to a number of reasons. Of course, the cost of natural gas is very cheap here, so it's harder. But we've seen the world in the last few years, as costs went down in renewable energy, major projects awarded by the government to basically through the reverse auction process. In fact, world lowest cost renewable projects happening in Saudi Arabia today. And the lowest one, I believe, was 1.6 cents a kilowatt hour awarded last year. And in Dubai, nearby, or in the Emirates, we saw 1.4 cent a kilowatt hour solar project. Similar prices on the megawatt or the gigawatt projects for wind in the region as well. The large land area, of course, the solar resources, and all are driving the costs of renewable electricity very low in this region. So we're expecting to continue seeing these record-breaking renewable costs, which, if you translate to in an energy basis from in the fossil fuel world, actually very competitive with natural gas-based or the cheapest natural gas-based powers. The challenge, of course, is the intermittency and the storage, which we see is quite significant, and therefore there's really going to be there has to be, especially for seasonal storage, not much. The daily storage might be achievable with relatively expensive storage, but we don't see the seasonal storage as being feasible for a long time to come, and that will require basically chemical energy storage. It'll have to require, I think, given the seasonal energy density requirements, you're going to need to store this either in a methane or into a liquid hydrocarbon, to be practical and that seasonal storage challenge is quite a challenge. We have, tremendous variations across the world. It's not just in the Middle East between winter and summer demand, for example. So you're basically idling all of your electricity use in the winter if you have much higher use in the summer. And the opposite happens in Europe, where you have huge demand of electricity in the winter and less perhaps in the summer. So this is the kind of challenges that we face across the world. And the only way to solve that right now is some kind of seasonal storage. And you're always going to need basically chemicals for that, I believe. I don't see any energy density practical for seasonal storage other than chemical energy. And therefore, you're going to need to unlock that chemical engine energy. So I do feel that we're going to have combustion in our power sector for a long time to come. I think it's going to be the most efficient option for seasonal storage. Now, that's not a big demand compared to, but it'll be a very important option to be able to make the economics work for grids. So I think it's either, there is, of course, beyond combustion, there's fuel cells, which are maturing, and we'll see them scale up. And ultimately, by 2050, I assume, we'll definitely see fuel cells, solid oxide fuel cells, and others, really a big part of the grid, in fact, not just the niche that their application right now, but perhaps to solve this challenge of intermittency. So I'm very confident that we'll be seeing chemical energy for a long time to come. And I think even Elon Musk agrees with me. A few days ago, he announced his $100 million X prize for carbon capture. I think he realizes that to get to Mars, you're going to need chemical energy. You need in fact, hydrogen won't cut it. It looks like the energy density of hydrogen is not that attractive, even in liquid form. Methane is much better from an energy density point of view, volumetrically. So, if you're trying to, you want to get the size of that spaceship small enough or big enough, whatever you want, you need the methane, you need that hydrocarbon. So the hydrocarbons are actually going to be with us for a long time to come, I believe, because of the amazing energy density in them. You asked about electrolyzers. We are not yet tested, but we have a number of projects in the works. As I mentioned, the Repsol project in Spain, where we are using electrolyzers to produce the hydrogen and therefore produce it through a Fischer-Tropsch process to produce liquid fuels. We're looking at sizes of around 50 barrels a day overall for now for pilot this technology, but that's very easy to scale up once the market takes off, and we think there will be a market for the blending of these fuels initially, and then long-term the use of them, especially in aviation where there aren't too many options. Biofuels are not the best option because of the chemistry. They are, very hard to mix them more than a certain percentage. Whereas we can design the e-fuels pretty much to be identical to existing jet fuels and existing gasolines. So that's one of the advantages of these e-fuels. Basically, they can meet all the specs as needed for the industries, and without, and we can be drop-in. At very large ratios and large percentages. So I personally believe that aviation will have to move for the next 20 years into a synthetic fuel approach to reduce its carbon footprint. I do believe biofuels are limited for a number of reasons, as we know, historically, agriculture and other reasons, the land limits, and the costs as well. The costs have not been taken into account when you look at a CO2 mitigation lens. So that's our view on the electrolysis. We do believe electrolysis is going to take off. We are supporting, we have a number of projects there. I'm confident that we'll see costs in the several $100s per kilowatt from reputable suppliers. Today in China, it's about $200 a kilowatt for electrolyzers. So it's extremely cheap. Globally, we see much higher prices. Hopefully, we'll see some of that technology around the world soon, and the cost will go down quickly.
Okay. On the issue about the e-fuels, the next question is from an anonymous audience. You might have answered most of that questions, but since this question is quite technical, let me ask it so that we get your response. If e-fuel or renewable fuels can be made to meet octane number and seating number targets, do you expect these fuels to be drop-in replacements, or what combustion problems do you foresee?
So I kind of touched on it, as you said. We can tailor the fuels like we tailor the existing fossil fuels, and even better. Because they're pure feedstock, we really don't have to do any kind of distillation, minimal distillation. In the methylene to gasoline, and the methanol to gasoline. But in the Fischer-Tropsch, there is some. Of course, you have to separate the products. But yeah, it's a much more, very similar to the gas to liquids projects that are around the world. The technology is very well mature. It's been around since World War II. And it's quite well understood. Full drop-in the case of the Fischer-Tropsch fuels, jet fuels, and such. We don't see any challenges actually out there. They have been utilized for years and years with no challenge with existing technology, combustion. So I think it's going to be less actually challenges than we have with existing fuels. Many of the existing fuels, as you know, are mixtures. They're boiling point ranges. These are much more pure chemicals than much tighter boiling point ranges. So the challenges are much easier to design and blend and mix to get the exact mixture that we're looking for. So it's actually, as I mentioned, it's more flexible. It's actually better from the challenge is economics. We expect these fuels to be in the perhaps 100 at this point in the pilots. We're looking at in the range of $150 to $200 a barrel. So initially, the costs are high for full drop-in, probably a challenge economically, but as a blend, very economic compared to alternatives. So when we look at the cost of alternative powertrain alternatives, the cost of mitigation of CO2 is in the hundreds of dollars per ton of CO2. So the battery options add a big cost to the vehicle, and therefore, if you look at the cost of that per ton of CO2 mitigated, a typical light-duty vehicle only puts out a few tons, 5-6 tons of CO2 per year. So it's adding a few $1,000s of battery to a car is hundreds of dollars per ton per year. Is the cost is hundreds of dollars per ton per year. So it's difficult. It's not the ideal solution, especially in where we have grids that are pretty carbon intense. You're just moving the carbon footprint from the car to the power plant, so it really doesn't help much. Relatively very little CO2 mitigation with the solutions that are being offered today. Now, as intensity of the grids goes down over time, it will have more and more impact.
Very good. You actually anticipated the next question that will come your way. This question is asked by Professor Asa Masari of the University of Sydney, who gave the plenary talk this morning, actually, on many issues concerning e-fuels, the basic research questions. Professor Masari's question is, many car manufacturers are drifting towards BEVs. Would they adopt e-fuels and continue with ICE manufacture? What does it take for this to happen?
Okay, so we see that, and that's because they really don't have any options but BEVs to lower their carbon footprint. So, as I mentioned before, efficiency to meet the strict standards that are being applied, there's really no option. We know efficiency limits of internal combustion engines are in the say 40 to 50% for transport. And so beyond that, they really have no options other than battery electric vehicles, and the penalties are quite severe, especially in Europe, for exceeding the efficiency requirements. The challenge, of course, is that the efficiency standards, as we see them globally, are only tank to wheel. So, in fact, there's no credit given for any reduction of efficiency upstream of the vehicle. And so even if you bring in a negative emission fuel, if there was such a thing, it has no impact, or a zero emission fuel, let's put it correct. It doesn't help the automakers at this point because the regulations don't recognize those lower carbon footprints as contributing to their efficiency standards or their mileage, the CAFE standard, for example. Whereas on electric vehicle counts automatically in most standards around the world as 0 miles, basically a 0 miles credit. It's more complex than that. I'm going to simplify it. Many of you understand this much better than I do, so I won't get into the detail. But the fact is, electric vehicles are given a pass when it comes to carbon footprint. They don't take the carbon footprint of the power. They're not responsible for the carbon footprint of the power. So in fact, basically, combustion is competing with one arm tied behind its back. Okay, so for the automakers, the regulations have to change to recognize the full life cycle of the powertrain. So from well to wheel, if they would recognize the carbon footprint of the full powertrain, then it would be a level playing field. And they would be able to continue to utilize some of their technologies and advance their technologies with an understanding that they're going to have a place in the market. Today, they see no place in the regulations for any combustion. And that's why they, even though they recognize there's huge value in much more efficiently reducing of the carbon footprint or the carbon emissions from transport through developing their existing platforms, if it's not going to get any credit for it in any of the standards or regulations, why should they do that? So they're moving to, now, if regulations were to change, do I think the automakers would respond? In some cases, automakers have actually completely disbanded their whole design teams in cases and actually, laid off workers. So it's difficult for them to come back in a few cases. I won't mention names, but there are. But I think that once the regulations are changed in a logical way, which gives the full life cycle value, carbon footprint credit, we will see many going to develop their powertrains and work toward, because it is the best option. Today, we know that most of the profits of automakers come from their combustion engines, the SUVs, which are actually creating greater carbon footprint because of that fact. They're large engines and inefficient, and they don't need to develop them any better because they're selling a small number of electric vehicles, which can balance out the emissions from that. And their CAFE standard looks great. But in fact, their real emissions, their total real emissions, the power plant emissions, the incremental additional power plant emissions needed for the electric vehicles they sell, plus the higher SUV, is much beyond what the CAFE standard was meant to address. So the CAFE standard is not a good tool, as they are, to address emissions. Emissions have to be addressed with new regulations, which are specific for the full life cycle. And we will see many choose to actually improve their existing engine platforms and therefore bring down meet the standards if they would be given credit for that full life cycle and compete. Because the difference is not much in most countries between an electric vehicle and a hybrid, for example. In fact, in some countries, the hybrid has less emissions full wheel life cycle. Many places, I think in China, for example, we have seen that the hybrid electric vehicle, based on the carbon intensity of the grid, is less. It has less CO2 per kilometer emitted than electric vehicles. It's just because of the hybrid just happens to have a higher efficiency than the power plant. That's from as simple as that from a CO2 point of view. Less CO2 emitted from the hybrid car than engine than and if regulators would recognize that, they would make more practical policies, which would, I think, drive the carbon footprint to go down faster.
Yeah, your point about the life cycle analysis, well-to-wheel analysis is very critical in this whole equation. And often, as we all know, what sounds good, looks good, might not be the best solution. So what I hope to see is that this research community, who are well-trained in thermodynamics, can help in this effort in educating policymakers to make the most rational decision. So I have one more question for you. We have about 10 minutes.
Sure.
Great, thank you for leaving time for the audience to ask a question. And this is very nice to see that we have this forum for chatting questions that I have in mind and getting your take on various things that we've been thinking about. So the next question, then perhaps the last question, is from Professor Bassam Daly, actually the local virtual organizer of this combustion symposium. He has two questions for you. The first question is, does Saudi Aramco has its own targets in terms of a carbon reduction? And if so, is it more on its processes or in reduce the carbon fuels? For example, blending with e-fuels. There seems to be a lot of interest in e-fuels, as you can see. The second question is, there seems to be two views about alternative marine fuels, methanol and ammonia. What is your view?
Okay, two very good questions, actually, and very interesting topics. First of all, on the carbon footprint for the company. So the company, of course, has been investing in environmental solutions for a long time. In fact, I would say our history of environmental investment in addressing environment precedes much of the discussion we have today. So, and it shows in our results. So we've published our carbon footprint for Saudi Aramco's oil production. So we are the world's lowest carbon emitter in production of oil. We're about 10.4 kilograms of CO2 emitted for each barrel of oil we produce. That's from the well to the refinery gate. So that includes the transportation to the refineries of the world. So that's an extremely low number. I guess we're matched by Equinor. Equinor has a similar number, and Equinor has similar history as well. But of all the major oil companies in the world, we are by far the lowest. The average for that upstream production or emissions associated with production of oil it's hard to get because not everybody publishes, but what we have seen from some of the published literature is about 40 to 60 kilograms of CO2 emitted for every barrel on a world average. That means that we're really we're the closest. I would say we're the closest to net zero production, because of course that last 10 kilograms is really tough to reduce, but we're working on it as we speak. In fact, a lot of our research is on how to really reduce that last bit of emissions. And the way, I would say there's a number of reasons we have achieved that. One, of course, is we put a lot of effort and technology in the subsurface where the energy is mostly expended. So for example, we have much costlier wells. We put in a lot of technology to shut off production that's unwanted, such as water production, gas production. We have a lot of simulation technology that we apply to maximize production from each well, and that lowers the energy per well. So that ends up with, for each barrel we produce, very little energy is utilized to get the barrel out. There's some geology, some favorable geology that works in our favor, but if you look at our neighbors who have the same geology, you'll see that they are some of the world's highest emitters of CO2 per barrel. So it's not just geology. In fact, it is investment and philosophy and operational methodology and technology. I have to emphasize the technology aspect. We apply the world's most powerful simulators to TerraPowers, which is a trillion cell simulator. We've been running these since the 70s and 80s, the simulators that allow us to simulate the flow in the subsurface of our oil, and therefore we optimize the flow to have the lowest energy requirement. And so we end up basically with a world with an average. If you understand the oil industry, a lot of the energy is actually water injection to provide the pressure for the oil to be produced. So we produce 3 barrels of oil for every barrel of water we inject. The world average is actually 3 barrels of water for every barrel of oil produced. So you can see that we really work, we invest a lot in reducing the energy to produce our product, because we understand that the cost of the product actually is driven by that energy. And so we therefore have the lowest cost per barrel. So good environment leads to good economics and good business, and so we have the lowest cost barrel. We're in the several dollars per barrel cost of production, a few dollars per barrel cost of production, and that is really a function of the energy we use. We use very little energy to produce the barrel of oil. Now, the other aspect I would say that allowed us to achieve this very large was a very early decision in the Kingdom of Saudi Arabia, actually by the government in the 1970s, to regulate the flaring of natural gas. At the time, the Gulf region, was the brightest region that could be seen from space because of the flares. All the associated gas was being flared in this region. And if you recall the photos from Skylab and from, they would always take photos of the Gulf region, the Arabian Peninsula, because it was all lighted, and in the evening it looks really nice. But in fact, it was a tremendous waste of energy and a huge environmental damage in our views of the gas, the methane that was being burned. And so we started the Master Gas System, the Master Gas Program. The company is invested billions and billions of dollars in one of the largest engineering projects in the world to gather the gas from across the kingdom and utilize it in the production of chemicals like methanol, like plastics and polymers and such. And what was zero value became one of the most important sectors of our economy today, which is petrochemicals, mainly from the gas that was collected during that program in the 70s. But it had the benefit, of course, of reducing our methane emissions and our CO2 emissions tremendously, which gets us to this 10 kilograms today. So much of the other oil makers continue to flare associated gas, especially in the US, and therefore you get very high emissions per barrel. And so I think we are some of the world's best. We are the world's best, we believe, for major oil companies in reduction, and we continue to work on reducing that. We don't talk too much about it, but we are going to be presenting that more and more often in in our publications and in our reporting. And we do third-party assessments of our, for those, because we understand there's, we have it looks good for us, of course, but we have third-party assessments to assess all of our reporting of our emissions. And we're very proud of our performance over the last few years. Now, you asked another question about methanol or ammonia. I'm kind of a fan of ammonia, just because you don't have to capture the CO2. So it's, if I looked at the fact is that when you burn the ammonia, you get nitrogen and no CO2. So the methanol is equally viable as a synthetic fuel for shipping, but you still have that CO2 footprint. It's maybe a quarter less. You have to recycle it somehow. The nice thing about ammonia is you don't have to capture the CO2 to make it. You can just, the air is, nitrogen is 75% or 80% of the atmosphere. So it's much cheaper to recycle the nitrogen into ammonia, to produce ammonia, than it is to recycle the CO2. But we're getting there on the CO2. So one day I'm going to be pro-methanol probably. But I think right now I'm a little more for ammonia. And we're looking at a very interesting study, which is looking at carbon capture on board ships. We've been doing a lot of carbon capture, mobile carbon capture. We did it on a light duty vehicle, about 10 years ago or so on a Toyota Camry. And we captured about 25% of the CO2 coming out and stored it on board. Recently, we showed a Class 8 truck in the U.S. where we captured about 45% of the CO2 on board, and without much modification of it. It's basically an after. Basically a carbon capture unit on the exhaust of the engine. And now we're looking at ships, and on ships it becomes actually quite economic, quite attractive, because of the large scale of the engines and the large scale of the volume actually makes the cost come down dramatically in the capture equipment. So it may be a very good option, actually, capturing CO2 on board and unloading where you have carbon sequestration options, which happens to be in many places where we are actually supplying the fuel anyway. So it's nice. It might work, where we have a number of studies going in that area.
Very good. That said, on behalf of the audience, I wish to thank you again for coming to speak to us and for having this wonderful, productive conversation. Thank you.
Thank you.
And this
thank you very much.
Current industrial session, and I think we have a certificate for you.
That's great.
Signed by ex-president of the Combustion Institute, Professor Jim Driscoll.
Excellent. Thank you very much. It's nice to have a virtual certificate. I'm sure I'll get the physical one in the mail. Thank you.
I'll make sure you have the physical. Thanks.
Thank you. Great to see you all. Bye.
Thank you for all the audience for joining us. Bye-bye.